I'm so glad you found your way here, beneath your feet right now. Earth is slowly transforming carbon into diamonds under tremendous pressure, a process happening in darkness beyond our sight, taking millions of years. You'll discover how crystals hold Earth's deepest secrets and understand why the most beautiful things require the longest patience. Welcome to Get Sleepy Science. Wherever you are right now, perhaps noticing light reflecting off a window or holding something cool and smooth in your hand, allow yourself to settle into this moment. We'll explore 100 Earth science facts about crystals and their hidden wisdom. From atoms arranging themselves into perfect patterns deep underground, to light bending through transparent structures, to the silent patience of minerals waiting millions of years to form. These calm explorations of Earth's crystalline wisdom plant seeds of tranquility in restless hearts. A gentle like, subscribe, or sharing this science creates a pathway for more curious souls to discover and brings us closer to protect this healing ground. One sleepy soul at a time. Your presence here means the world to this peaceful space. Sink into your favorite resting spot. Allow your muscles to release, each breath growing softer. There's no need to remember these geological facts. Just notice that warm, drowsy calm washing over you, like gentle ocean waves pulling back from shore. Each one drawing you deeper into restful, effortless sleep. Close your eyes and breathe deeply. You're resting where ancient stones whisper secrets of eternal patience. Let your mind sink with nature's calm. And now we begin. A crystal is simply matter arranged in perfect order. At the most fundamental level, crystals are atoms or molecules organized in repeating three-dimensional patterns that extend in all directions. This arrangement isn't random or chaotic like most materials around us. Instead, imagine a dance where every participant knows exactly where to stand, creating a pattern so precise it can repeat infinitely. According to the International Union of Crystallography, this ordered internal structure is what makes true crystals different from other solids, creating the geometry we recognize. Whether it's the salt on your dinner table, the quartz in your watch, or the diamond in a ring, each crystal type follows its own specific geometric rules. The atoms lock into place like puzzle pieces, forming structures that can persist for billions of years. This beautiful order arises naturally, without any conscious design, simply from the laws of physics and chemistry acting on matter as it cools or solidifies. Crystals form when conditions are just right for atoms to settle into their lowest energy state. Think of it like people in a crowded room trying to find comfortable spots. Everyone naturally moves to where they feel most stable. For crystals, this happens when molten rock cools slowly, when mineral-rich water evaporates, when underground pressure changes, or when gases condense. The slower the process, the larger and more perfect the crystals can grow. Recent research from the Geological Society of America shows that some crystals found in pegmatite formations grew over periods spanning millions of years, adding layer upon microscopic layer with extraordinary patience. Fast cooling produces tiny crystals, or none at all. That's why volcanic glass lacks crystal structure, despite being made of the same minerals as granite. Nature seems to reward patience with perfection, a lesson written in stone throughout Earth's crust. There are 7 basic crystal systems that all minerals follow: Crystallographers have identified these fundamental geometric patterns: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. Each system describes how atoms can arrange themselves in three-dimensional space while maintaining symmetry. A cubic crystal like salt or diamond has atoms arranged in perfect squares from every angle. Hexagonal crystals like quartz form six-sided structures. Monoclinic crystals have slightly tilted angles, creating structures less symmetrical but equally stable. According to studies published in the American Mineralogist Journal, despite Earth's immense diversity of minerals, over 5,000 types identified, they all conform to these 7 basic architectural blueprints. It's remarkable that such variety emerges from just 7 fundamental patterns. Like infinite stories written with the same alphabet, the universe seems to prefer elegant simplicity underlying apparent complexity. The largest natural crystals ever found are in Mexico's Cave of Crystals, discovered in 2000 in the Nika mine of Chihuahua. These selenite gypsum crystals reach lengths exceeding 36 feet and weigh up to 55 tons. The cave sits nearly 1,000 feet below the surface, where temperatures reach 136 degrees Fahrenheit with 90 to 100% humidity. Conditions so intense that humans need cooling suits after just 15 minutes. An environment more suited to mineral growth than human presence. According to research published in Geology magazine, these giant crystals grew in a water-filled cave over roughly 500,000 years, forming when mineral-rich groundwater maintained stable temperatures between 136 and 158 degrees Fahrenheit. When mining operations accidentally drained the water, growth stopped. The crystals now exist in an environment they weren't designed for, slowly beginning to deteriorate, reminding us how fragile even the mightiest structures can be. Diamonds form under incredible pressure deep in Earth's mantle, at depths between 87 and 118 miles beneath the surface, where temperatures exceed 2,000 degrees Fahrenheit and pressure reaches 58,000 atmospheres. Carbon atoms bond in the strongest arrangement known to nature. Research from the Gemological Institute of America indicates most natural diamonds are between 1 and 3 billion years old. They form slowly in the mantle, then ride to the surface during violent volcanic eruptions in rare rock formations called kimberlite pipes. The journey upward happens quickly. Geologists estimate the ascent takes just hours at speeds exceeding 25 miles per hour. Most diamonds reaching the surface were formed long before the first animals walked on Earth, carrying with them a record of conditions in realms humans will never visit. Silent witnesses to our planet's ancient, hidden heart. Snowflakes are crystals of ice that form unique patterns in clouds. Each snowflake begins around a tiny particle of dust or pollen suspended in freezing air. As water vapor condenses and freezes onto this nucleus, it follows the hexagonal crystal structure that ice molecules naturally prefer. According to atmospheric research from the National Center for Atmospheric Research, the specific shape each snowflake develops depends on temperature and humidity during its fall through different cloud layers. At around 27 degrees Fahrenheit, snowflakes form thin plates. Near 5 degrees, they become slender needles or columns. Between 15 and 25 degrees, especially around 23 degrees, they create the classic six-pointed stars we recognize. The famous saying that no two snowflakes are identical is likely true. with trillions of possible molecular arrangements and unique atmospheric journeys. Each crystal becomes a one-of-a-kind frozen sculpture, perfect and temporary, melting back into formless water within moments of landing. Quartz is the second most abundant mineral in Earth's continental crust, comprising approximately 12% of the continental crust by volume. Quartz appears in countless varieties, from clear rock crystal to purple amethyst, pink rose quartz to smoky brown citrine. According to the Mineralogical Society of America, quartz's chemical formula is simply silicon dioxide, the same compound found in sand on beaches worldwide. Its abundance stems from silicon and oxygen being the two most common elements in Earth's crust. Quartz crystals form in igneous rocks like granite, in sedimentary rocks like sandstone, and in metamorphic rocks like quartzite. They resist weathering better than most minerals, which is why quartz grains dominate many sand deposits. Walking on a beach, you're likely walking on countless tiny quartz crystals, each one a miniature geometric marvel, shaped by the same laws governing massive crystal formations deep underground. Salt crystals form when seawater evaporates. As ocean water sits in shallow pools warmed by sunlight, the water molecules escape into the air as vapor, but the dissolved sodium and chloride ions remain behind. When the water evaporates and salt concentration increases beyond what the liquid can hold, reaching about 26% for sodium chloride, the ions begin bonding into solid cubic crystals. Research published in the Journal of Crystal Growth shows this process happens continuously in coastal salt pans and natural evaporite basins worldwide. Each salt crystal that forms is a perfect cube at the molecular level, though larger crystals may appear as hollow pyramids or stepped structures depending on growth conditions. Ancient salt deposits, buried underground, some hundreds of millions of years old, formed this same way when ancient seas evaporated. The salt you sprinkle on food today may contain crystals that first formed when dinosaurs walked the earth, preserved perfectly in darkness, waiting. Crystals can grow, but not like living things grow. Crystal growth is purely physical. Atoms or molecules from the surrounding environment attach to the existing crystal structure, extending the pattern outward. A crystal in a saturated solution will slowly add layers, growing larger while maintaining its geometric form. According to research from the American Association for Crystal Growth, growth rates vary enormously. Some crystals in caves grow less than 1 millimeter per 1,000 years. Others in laboratory conditions can grow several inches in days. Unlike biological growth requiring complex cellular processes and genetic instructions, crystal growth is simply matter finding its most stable arrangement. There's no metabolism, no energy consumption beyond the physical chemistry of bonding. A crystal growing in a cave doesn't know it's growing, doesn't want to become larger. It simply is, expanding grain by grain into the darkness, patient and unconscious. So yes, crystals are already revealing something profound about order emerging from chaos. We've discovered that nature, left to its own devices, tends toward organization when conditions allow. From the perfect hexagons of snowflakes to the cubic precision of salt, from diamonds formed in tremendous pressure to quartz grains beneath our feet, crystals demonstrate that beauty and order arise naturally from simple physical laws. No consciousness designs them, no intelligence guides their formation. just atoms following the basic rules of chemistry and physics, finding their lowest energy state, creating structures of remarkable regularity and elegance. This suggests something fundamental about our universe, that complexity and beauty are not rare anomalies requiring special explanation, but natural consequences of matter interacting with itself over time. Even chaos, given enough time and the right conditions, crystallizes into order. Ice crystals in your freezer form the same hexagonal structure as snowflakes. When you freeze water, the molecules arrange themselves in a crystalline lattice with six-fold symmetry. The same pattern, whether you're making ice cubes or examining frost on a window. According to research in the Journal of Physical Chemistry, this happens because water molecules are shaped like Mickey Mouse ears, with oxygen as the head and two hydrogen atoms as the ears. When freezing, these molecules link together in a way that creates maximum stability, and that geometry happens to be hexagonal. Interestingly, ice is actually less dense than liquid water because the crystal structure creates open spaces between molecules. This unusual property, solid being less dense than liquid, is why ice floats, why lakes freeze from the top down, why aquatic life can survive winter beneath a protective, frozen ceiling. Amethyst gets its purple color from iron impurities and natural radiation. Pure quartz is colorless. But when trace amounts of iron are present during formation, the crystal lattice incorporates these foreign atoms. Over millions of years, natural radiation from surrounding radioactive elements alters the iron atom's electron configuration, creating the distinctive purple hue. Research from the Gemological Institute of America shows that heating amethyst above 900 degrees Fahrenheit can change it to yellow or orange citrine by altering those electron configurations again. Ancient Greeks believed amethyst prevented intoxication. The name comes from the Greek word amethystos, meaning not drunk. While that belief was mistaken, there's something sobering about holding a stone that owes its color to atomic radiation, slowly working its transformation over geological timescales we can barely comprehend. Crystals have defined angles between their faces that are always the same for each mineral. This principle, called the law of constancy of interfacial angles, was discovered by Nicholas Steno in 1669 and remains fundamental to crystallography. A quartz crystal from Brazil will have the same angles between corresponding faces as a quartz crystal from Arkansas, regardless of size or overall shape. According to the International Union of Crystallography, these angles are determined by the internal atomic structure. Since the atoms are arranged in identical patterns, the crystal faces that develop naturally reflect that underlying geometry. Crystallographers use these angles to identify unknown minerals, measuring them precisely with instruments called goniometers. It's remarkable that something so precise emerges from natural processes, that nature can be so consistent, creating the same geometric relationships repeatedly across continents and eons, following invisible mathematical rules encoded in atomic bonds. Gemstones are simply minerals that are beautiful, rare, and durable enough to be valued. The distinction between a gem and a regular mineral is mostly human preference. Rubies are corundum with chromium impurities. Sapphires are corundum with iron and titanium. According to the International Gem Society, about 100 minerals out of over 5,000 known species are considered gemstones. Diamond, ruby, sapphire, and emerald are termed precious stones, while all others are semi-precious. Though this classification is somewhat arbitrary and old-fashioned, what makes a gem valuable is rarity, hardness, clarity, color, and cultural significance. A perfectly formed quartz crystal might be scientifically identical to an amethyst gemstone, but the color makes one valuable and the other common. Humans have projected meaning onto certain crystals for thousands of years, seeing beauty in arrangements of atoms that know nothing of beauty, creating worth from geological accident. Crystal faces form because certain atomic planes are more stable than others. As a crystal grows, atoms attach more readily to some surfaces than others, creating flat faces where growth temporarily slows or stops. Research published in Nature Materials explains that these faces represent planes where the atomic structure is particularly dense and stable. Imagine stacking oranges in a grocery store. Certain arrangements create naturally flat surfaces. Similarly, atoms stacking in three-dimensional patterns create preferred surfaces that appear as crystal faces. The beautiful geometric shapes we associate with crystals, the points of quartz, the cubes of pyrite, the octahedrons of diamond, all emerge from this interplay between atomic structure and growth conditions. No artisan carves these shapes. No designer plans these forms. They simply emerge as matter seeks stability, creating accidental geometry that humans later find aesthetically pleasing, meaning arising from meaningless chemical bonds. Crystals can contain records of Earth's magnetic field from when they formed. Certain minerals like magnetite incorporate tiny magnetic domains that align with Earth's magnetic field during crystallization. Once the crystal solidifies, this magnetic orientation is locked in place, creating a permanent record. According to paleomagnetism research published in Geophysical Research Letters, scientists can determine the latitude where rocks formed millions of years ago by analyzing these magnetic signatures. This has revealed that continents have drifted across Earth's surface, that magnetic poles have reversed hundreds of times, that the magnetic field has varied in strength throughout geological time. Ancient crystals become tiny compasses pointing toward poles that no longer exist in those positions, silent witnesses to a restless planet's magnetic dance, preserving in their atomic structure a history that predates human memory by incomprehensible spans. Some crystals are piezoelectric, meaning they generate electricity when squeezed. Quartz exhibits this property particularly well. Applying pressure deforms the crystal structure slightly, shifting the positions of positive and negative charges and creating a voltage. According to research from the Institute of Electrical and Electronics Engineers, this effect also works in reverse. Applying voltage causes the crystal to change shape. This property makes quartz essential in modern electronics. Quartz watches use this effect to keep time. An electrical current makes the crystal vibrate at precisely 32,768 times per second, providing a stable frequency reference. Piezoelectric crystals also appear in microphones, speakers, sonar, and medical ultrasound devices. It's remarkable that a property of atomic structure discovered in certain minerals has become fundamental to modern technology. That the same stones ancient humans picked up unknowingly contain capabilities we now harness to communicate and navigate. Crystal cleavage describes how minerals break along specific planes. Some crystals break cleanly along flat surfaces parallel to their faces. while others fracture irregularly. According to the Mineralogical Society of America, cleavage occurs along planes where atomic bonds are weakest. Mica demonstrates perfect cleavage, splitting into paper-thin sheets because its atomic structure consists of strong bonds within sheets, but weak bonds between them. Diamond, despite being the hardest natural substance, has cleavage planes where a sharp blow can split it perfectly. Diamond cutters use this property to shape rough stones. Other minerals like quartz have no cleavage, breaking with curved, irregular surfaces called conchoidal fracture. How a crystal breaks reveals its internal architecture. The invisible weakness between atoms becoming visible when enough force is applied. Structure determining destiny, even in dissolution. Crystals can form inside other crystals, creating beautiful inclusions, sometimes called phantom crystals or rutilated quartz. These occur when crystal growth pauses, conditions change, and growth resumes with different chemistry. The earlier crystal becomes frozen inside the later one, preserved like an insect in amber. Research published in Mineralogy and Petrology shows that some inclusions are older than their host crystal by millions of years. A fragment of ancient crystal serving as a seed for new growth. Rutilated quartz contains needle-like crystals of titanium oxide inside clear quartz, creating golden threads frozen in glass. These accidents of geology create unique beauty. No two specimens identical. Jewelers sometimes value included crystals more than perfect clear stones, because the inclusions tell stories of interrupted growth. Changing conditions, geological events frozen mid-occurrence, time's passage written in solid matter. The hardness of minerals is measured on the Mohs scale from 1 to 10, developed by German mineralogist Friedrich Mohs in 1822. This scale remains the standard method for classifying mineral hardness. Talc rates 1, so soft you can scratch it with your fingernail. Diamond rates 10, the hardest natural substance known, according to the International Mineralogical Association. Each mineral on the scale can scratch all minerals below it. Quartz, at 7 scratches window glass. Your fingernail is about 2.5. This scale is relative, not linear. Diamond is actually about 4 times harder than corundum at 9. The scale works because hardness reflects bond strength in the crystal structure. Stronger atomic bonds create harder materials. Your fingernails and diamonds differ not in kind, but in how tightly their atoms cling together. A continuum of cohesion from soft to adamant. Crystals grow in specific environments called facies based on temperature and pressure. According to metamorphic petrology research, different minerals are stable under different conditions. Garnet forms under high pressure. Zeolites form at low temperatures. Andalusite, kyanite, and sillimanite are all chemically identical but have different crystal structures depending on formation conditions. Geologists use these indicator minerals to reconstruct the temperature and pressure conditions that existed deep in Earth's crust millions of years ago. A rock containing both garnet and kyanite tells a story of considerable pressure and moderate temperature. These mineral assemblages are like frozen thermometers and barometers, recording conditions from environments no human will ever visit, preserving in solid form the specific combination of heat and pressure that existed at the moment of their formation. Evidence of deep earth processes written in durable stone. Some crystals are fluorescent, glowing under ultraviolet light. This happens when UV photons excite electrons in the crystal to higher energy states. Then the electrons release that energy as visible light when falling back to ground state. According to research published in the Journal of Luminescence, fluorite, calcite, willemite, and many other minerals exhibit fluorescence, sometimes in spectacular colors, invisible in normal light. Scheelite glows blue-white under UV light, making it easy to find in dark mines with UV lamps. Some diamonds fluoresce blue. The phenomenon seems magical, but is pure physics. Photons in, higher energy electrons briefly. Photons out at different wavelengths. Certain crystals absorb invisible light and emit visible light, transforming radiation we cannot see into colors we can perceive, acting as natural converters between different portions of the electromagnetic spectrum, revealing hidden dimensions of light. Twinned crystals form when two or more crystals grow together in a symmetric pattern. According to the American mineralogist, twinning occurs when crystal growth is disrupted and resumes in a different orientation, often creating mirror image or rotated patterns. Starrelite commonly forms cross-shaped twins, creating natural crosses that medieval Christians believed had religious significance. Gypsum forms distinctive swallowtail twins. Some twins form during growth, others from deformation after formation. The resulting shapes can be more complex and interesting than single crystals, though they indicate imperfect growth conditions. These accidents create some of nature's most aesthetically striking forms. Two perfect structures joined imperfectly, each following its own geometric rules while connected at a boundary. Separate yet unified. Distinct yet inseparable. A duality frozen in stone that seems almost symbolic of relationships. Partnerships. The beautiful complexity arising when two ordered systems merge. Liquid crystals exist in a state between solid crystal and liquid. These molecules maintain some crystalline order while still flowing like liquids. A property discovered in 1888 by Austrian botanist Friedrich Reinitzer. According to research in Liquid Crystals Journal, these materials align in response to electric fields, which is why they're perfect for displays. Your phone or computer screen likely uses liquid crystal technology. Millions of tiny liquid crystal cells that rotate polarized light when voltage is applied, creating images. The molecules are elongated and rod-like, naturally aligning in parallel like logs floating in a river. But this alignment can be controlled electrically. It's a strange middle state, neither fully ordered like a solid crystal, nor fully random like a liquid, existing in a twilight zone of partial order. Stability mixed with fluidity. Control emerging from chaos. These observations reveal that crystals are not static, lifeless rocks but dynamic records of Earth's processes. Yes, they're solid and enduring, lasting far longer than any living thing. But each crystal tells a story of the temperature and pressure where it formed, of the chemicals present in that ancient environment, of the time it took to grow, of the geological events it witnessed. Crystals from the same mountain formed under identical conditions will have matching properties and structures. A kind of geological kinship. Those from different regions or depths will differ in predictable ways based on their formation history. So in understanding crystals, We're really learning to read Earth's autobiography, written in mineral code. Deciphering messages written in atomic structure millions or billions of years ago. Letters from the deep past, composed in the silent language of stone. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside. Trillions of organisms working in silence. Heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. You are a complete ecosystem, diverse, self-balancing. Now we continue. Crystals can bend light in fascinating ways. When light passes through a crystal at an angle, it slows down and changes direction, a phenomenon called refraction. According to optical mineralogy research, different minerals bend light by different amounts, measured as their refractive index. Diamond's high refractive index of 2.42 is why diamonds sparkle so brilliantly. Light entering bends sharply, bounces around inside, and exits at angles that create flashes of color. Quartz has a lower refractive index of 1.54, creating gentler optical effects. Some crystals are birefringent, splitting light into two rays that travel at different speeds, creating double images when you look through them. Calcite demonstrates this beautifully. Place clear calcite over text and you'll see every letter doubled. Two parallel realities visible simultaneously through transparent stone. Some crystals change color when heated. Amethyst turns yellow above approximately 900 degrees Fahrenheit, becoming citrine. Some blue topaz was originally colorless topaz exposed to radiation and heat treatment. According to gemology research, these color changes reflect alterations in the electronic structure that cause light absorption to shift to different wavelengths. Natural processes can create the same changes over geological time. Some citrine in nature formed as amethyst that was heated by nearby magma intrusions or metamorphic events. The colors we see aren't inherent to the crystal's chemistry but to its electronic state, which can be modified. Heat doesn't change what the crystal is made of, just how its electrons interact with light, proving that color is not substance but relationship between matter and energy. Crystal lattices can trap and hold other atoms, creating beautiful color varieties. Ruby is corundum with chromium impurities, replacing some aluminum atoms in the crystal structure. About one chromium atom per several hundred aluminum atoms creates the deep red color. Sapphire is the same mineral with iron and titanium impurities, creating blue. Emerald is beryl with chromium or vanadium. According to the Gemological Institute of America, these trace elements, sometimes less than 1% of the crystal, determine the color and value. Pure corundum is colorless. It's the imperfections, the foreign atoms incorporated during growth, that create beauty and worth. The flaws make the gem precious. The contamination creates value. Perfection would be clear and common. Impurity creates rarity and desire. Crystals can exhibit optical phenomena called pleochroism, showing different colors from different angles. This occurs in anisotropic crystals, where light vibrating in different directions is absorbed differently. Tanzanite, for example, appears blue from one angle, violet from another, and burgundy from a third. According to optical mineralogy research published in Elements magazine, This happens because the crystal's internal structure isn't uniform in all directions. The spacing and arrangement of atoms differ along different crystallographic axes. Gemologists examine pleochroism to identify unknown stones, using polarized light to reveal the hidden directional properties. It's as if the crystal contains multiple colors simultaneously, revealing different aspects of its nature depending on your perspective. Teaching a kind of mineral relativism where truth depends on the angle of observation. Crystals can grow in hollow centers, creating geodes. These form when minerals deposit on the inside of a cavity in rock, often a gas bubble in volcanic rock or a dissolved fossil cavity in sedimentary rock. According to research in geology, mineral-rich groundwater seeps into the cavity and slowly deposits crystals pointing inward toward the hollow center. The largest geodes can be several feet across, containing thousands of quartz or amethyst crystals, all growing from the outside in. Breaking open a geode reveals a hidden crystal cave, a secret garden of minerals that grew in darkness, unseen for millions of years. The outside looks like an ordinary rock, giving no hint of the beauty within. Sometimes the most spectacular structures are completely hidden, requiring breaking to reveal. The orientation of crystal growth can reveal ancient environmental conditions. Stalactites and stalagmites in caves grow vertically because gravity influences how water drips and where calcite precipitates. Tree rings show annual growth patterns. Similarly, some crystals show growth bands revealing seasonal or environmental changes. According to research published in Chemical Geology, analyzing oxygen isotopes in these growth bands reveals temperature changes over the crystal's formation period. Ancient crystals can contain climate records from before human civilization, preserved in stone. A single crystal might record hundreds of thousands of years of environmental change, each microscopic layer a snapshot of past conditions. The entire structure, a geological diary written in chemistry. Patience made visible, time made solid. Halite, or rock salt, forms perfect cubes because of its internal atomic structure. Sodium and chloride ions alternate in a three-dimensional checkerboard pattern, creating cubic symmetry. According to structural chemistry research, this arrangement reflects the 6 nearest neighbors each ion has, 4 in a square plane, 1 above, 1 below. Growing salt crystals always form cubes or variations on cubic shapes. You can grow them yourself by evaporating salt water, watching as tiny, perfect cubes appear and expand. The visible shape directly reflects the invisible atomic geometry. There's something deeply satisfying about this connection between the seen and unseen. How the microscopic determines the macroscopic. How atomic bonds dictate geometric form. Pattern at one scale, creating pattern at another. Some crystals are hygroscopic, absorbing water from air. Halite dissolves in humid conditions. Calcite can react with acidic water, slowly dissolving. This is how caves form. According to karst geology research, limestone caves develop over hundreds of thousands of years as slightly acidic groundwater dissolves calcite in the rock, creating cavities that eventually become caverns. The same water, now saturated with dissolved calcite, deposits that mineral as stalactites, stalagmites, and flowstone, building new crystal structures in the very spaces dissolution created. It's a cycle of dissolution and deposition. The same water, removing and adding, creating beauty through loss and gain, simultaneously occurring. Caves carved by water that also decorates them. Crystals can record shock events in their structure when meteorites impact Earth. The tremendous pressure and heat can create unique crystal forms that don't exist under normal conditions. Compressed quartz shows distinctive planar deformation features. Microscopic parallel lines formed when the crystal lattice was compressed by incredible pressure. According to impact geology research, finding compressed quartz in a sediment layer provides strong evidence of meteorite impact. The Chicxulub impact 66 million years ago, which contributed to dinosaur extinction, left compressed quartz distributed globally in a thin clay layer. These compressed crystals preserve evidence of catastrophic moments, carrying in their damaged structure proof of violent events. Witnesses bearing scars, memory encoded in deformation, history written in wounds that never healed. Some crystals exhibit chatoyancy, a silky sheen that moves as the stone moves, tiger's eye, a form of quartz with fibrous inclusions, shows this beautifully. A bright band of light appears to glide across the surface as you rotate the stone. According to gemology research, chatoyancy occurs when parallel fibers or needle-like inclusions reflect light back toward the observer, creating a concentrated band of reflected light perpendicular to the fiber direction. Cat's eye chrysoberyl shows this effect so strongly, it's named for it. The moving light seems almost alive, as if something liquid flows through solid stone, an illusion created by rigid parallel structures interacting with light. Stillness creating the impression of motion through careful geometry. Crystals reveal the age of rocks through radiometric dating. Zircon crystals are particularly useful because they incorporate uranium atoms during formation but exclude lead. Over time, uranium radioactively decays into lead at a known rate. According to geochronology research published in Earth and Planetary Science Letters, measuring the ratio of uranium to lead in a zircon crystal reveals how long ago it crystallized. Some zircon crystals found in Western Australia are over 4.4 billion years old, nearly as old as Earth itself, the oldest terrestrial materials ever discovered. These ancient crystals are tiny time capsules. Their internal clocks started billions of years ago, still ticking through radioactive decay, measuring time in half-lives spanning hundreds of millions of years. Patient and precise. Crystal symmetry fascinates mathematicians and artists alike. The repeating patterns in crystals represent just 14 possible three-dimensional lattice arrangements. Discovered by Auguste Brevet in 1848, these 14 Brevet lattices combine with 32-point group symmetries to create 230 space groups. All the possible ways atoms can be arranged in three-dimensional repeating patterns. According to crystallography research, every crystal ever found or synthesized fits into one of these 230 categories. It's remarkable that infinite variety emerges from finite templates, that billions of mineral specimens worldwide all conform to these mathematical constraints. Nature's creativity works within strict rules, finding endless variation within bounded possibility. Freedom expressing itself through structure rather than despite it. Some crystals are phosphorescent, continuing to glow after the light source is removed. Unlike fluorescence, which stops immediately when UV light is turned off, phosphorescent minerals continue emitting light for seconds, minutes, or even hours. According to luminescence research, this happens when electrons are trapped in metastable energy states, slowly releasing energy as they return to ground state. Willemite and calcite can show long-lasting phosphorescence. This delayed light emission seems almost magical, a rock glowing in darkness without any visible energy source. The crystal stores energy from earlier light exposure and releases it gradually. A kind of geological battery, converting and time-shifting light energy, making the invisible visible, the past illuminating the present. Crystals can form from vapor without passing through liquid phase. This process, called deposition or desublimation, occurs when gases condense directly into solid crystals. Frost forming on windows demonstrates this. Water vapor in air contacts cold glass and crystallizes without first becoming liquid. According to atmospheric science research, snow crystals also form this way in clouds when water vapor deposits directly onto ice nuclei. Volcanic fumaroles create sulfur crystals this way as sulfur vapor emerges from vents and crystallizes in cooler air. The transformation from gas to solid bypasses the intermediate liquid state entirely, demonstrating that matter can transition between states in multiple pathways, that conventional progression isn't necessary, that shortcuts through the phases exist. We now understand that crystals are far more than pretty rocks. They're piezoelectric generators, optical devices, time capsules, environmental recorders, and technological enablers. They demonstrate fundamental principles of chemistry, physics, and mathematics. They preserve Earth's history in their structure and chemistry. They reveal that order emerges naturally from disorder, that beauty arises from simple rules, that time and patience create complexity. The study of crystals connects quantum mechanics to geology, connects atomic structure to mountain formation, connects pure mathematics to mineral collecting. Understanding crystals means understanding how matter organizes itself, how energy and matter interact, how time leaves its signature in solid form. We've discovered that these silent stones speak volumes if we learn their language. If you're still awake, still listening to Earth's crystalline secrets, that means curiosity hasn't fully rested yet. And that's okay. Take a gentle breath. Feel the weight of your body on the bed. Grounded like ancient stone, we're wandering through mineral wisdom together, you and I. Drifting through facts like sediment settling slowly through still water. There's no rush, no deadline, just the slow accumulation of knowledge. Layer by gentle layer, and we'll keep going. Slowly. Your smartphone contains over 30 different minerals. According to research from the U.S. Geological Survey, modern electronics require diverse elements: quartz for timing circuits, gallium for LEDs, tantalum for capacitors, rare earth elements for speakers and vibration motors, gold and copper for connectors. Each mineral had to be mined, processed, and refined. That small device in your pocket represents geological processes spanning billions of years and mining operations across every continent. The copper might come from Chile, the tantalum from Australia, the rare earths from China, the gold from South Africa. You're holding a condensed piece of Earth's crust. Elements from ancient supernovas, geological diversity from around the world, all assembled into one small technological miracle. Crystals enable fiber optic communication. Ultra-pure quartz glass fibers transmit light signals over hundreds of miles with minimal loss. According to telecommunications research, modern fiber optic cables can transmit data at speeds exceeding 400 gigabits per second. The internet you're using likely travels partly through glass fibers, purer than natural quartz. These fibers are so transparent that if seawater were this clear, you could see to the ocean floor in the deepest trenches. Creating such purity requires melting quartz in ultra-clean conditions, removing virtually every impurity. Your messages, videos, and searches travel as pulses of light through crystalline glass. Information encoded in photons racing through structured silica. Watches once used mechanical gears. Now most use quartz crystals. When you apply voltage to a quartz crystal cut in specific ways, it vibrates at a precise frequency. For watches, 32,768 times per second. Electronic circuits count these vibrations to track time. According to horological research, quartz watches, accurate to within 15 seconds per month, became common in the 1970s, making precise timekeeping affordable. Mechanical watches required skilled craftsmanship and regular maintenance. Quartz watches democratized accuracy through crystal physics. Time itself, once measured by pendulums and springs, is now measured by vibrating quartz. The heartbeat of sand transformed into chronometric precision. Hospital ultrasound machines use piezoelectric crystals. These crystals convert electrical pulses into sound waves above human hearing range, then detect the echoes bouncing back from internal tissues. According to medical physics research, modern ultrasound can image a developing fetus, detect tumors, or guide surgical instruments, all non-invasively using sound. The same property that makes quartz watches tick enables doctors to see inside living bodies without cutting or radiation. Pressure creates electricity. Electricity creates vibration. Vibration creates sound. Sound creates echoes. Echoes create images. The cascade of transformations begins with crystals responding to voltage, converting energy from one form to another, making the invisible visible through careful application of mineral properties. Lasers require precisely grown synthetic crystals. Ruby lasers use synthetic ruby crystals. Aluminum oxide with chromium as the gain medium. According to laser physics research, photons bounce between mirrors through the crystal, stimulating chromium atoms to emit identical photons in a cascade that produces coherent light. NdYAG lasers use synthetic crystals of yttrium aluminum garnet doped with neodymium. Growing these crystals requires careful control, uniform composition, minimal defects, specific sizes and orientations. Natural crystals have too many impurities and irregularities. Modern lasers demand perfection beyond nature's capability, driving development of crystal growing technology that surpasses geological processes in quality, if not patience. Crystals store computer data in flash memory drives. According to materials science research, flash memory uses silicon crystals with floating gates that trap electrons. The presence or absence of trapped electrons represents ones and zeros. Writing data means pushing electrons through an insulating layer where they remain trapped, preserving information even without power. Your USB drive, solid-state hard drive, and memory cards all use this technology. Information exists as patterns of trapped electrons in crystal structures. Knowledge, frozen in silicon. Thoughts encoded in charge distribution across atomic lattices. Memory made physical. Ideas solidified into manipulatable electron configurations. Consciousness translated into crystalline state. Solar panels convert sunlight to electricity using silicon crystals. These photovoltaic cells use silicon with carefully controlled impurities, creating a junction where electrons flow when photons strike. According to photovoltaic research, modern solar cells reach 20 to 25% efficiency, converting sunlight to electricity. Each panel contains millions of silicon atoms arranged in crystalline structure, their electronic properties tuned precisely. Sunlight that traveled 93 million miles through space strikes these crystals, transferring its energy to electrons, which flow as current. Ancient starlight captured by engineered stone and transformed into usable power. Photons becoming electrons. Light becoming lightning. Solar fusion energy harvested through crystalline semiconductors. Star power captured in sand. Synthetic diamonds now rival natural ones in quality and size. According to gemological research, chemical vapor deposition can grow diamonds atom by atom from carbon gas, creating stones chemically identical to natural diamonds. Some synthetic diamonds are purer than natural ones, lacking the nitrogen impurities common in mined diamonds. The distinction matters mainly for romance and tradition, not chemistry or appearance. Laboratory-grown diamonds form in days or weeks, not billions of years, but the resulting crystal structure is identical. Time becomes irrelevant when humans replicate geological processes, when patience is replaced with engineering, when ancient depth is mimicked in controlled chambers. Crystals detect radiation in medical imaging and security scanners. Scintillation crystals like sodium iodide emit light when struck by X-rays or gamma rays. According to radiation detection research, these crystals convert invisible radiation into visible light photons that can be detected and counted. CT scanners use scintillation crystals to measure X-rays passing through the body. Security scanners use them to inspect luggage. Even the detectors aboard space telescopes use crystal scintillators. The crystals act as translators, converting one form of energy into another, making the invisible detectable, the dangerous measurable, turning radiation's chaos into ordered light pulses we can count. Halfway through our journey, we've seen that crystals bridge nature and technology. They grow in caves and power our devices, form in pressure depths and enable our communications, crystallize over eons and measure our seconds. This connection between geological processes and human innovation reveals something profound. The same physical laws govern both. Whether atoms arrange themselves deep in Earth's mantle over millions of years or in a laboratory chamber over days, they follow identical principles. Humans haven't conquered nature. We've learned to work with it, to accelerate what patience accomplishes slowly, to recognize that understanding nature's methods means gaining nature's capabilities. Science as apprenticeship to time. And imagine, even when everything seems empty, space is always full of waves, vibrations, invisible energy. The space inside and around you is never truly empty. Imagine you're floating on a calm lake. But beneath the surface, there's always gentle current, always movement you cannot see. Like crystals forming in darkness beneath mountains, processes continue unseen, unnoticed, patient and persistent. Now we continue the journey. Crystals can be millions or billions of years old. The oldest mineral grains found on Earth are detrital zircons from the Jack Hills of Australia, dated at approximately 4.4 billion years old, formed just 160 million years after Earth itself. According to research published in Nature Geoscience, these ancient crystals survived the complete melting and recycling of the rocks that originally contained them, weathering out and being incorporated into younger sediments multiple times. They witnessed Earth's entire history from a molten beginning, persisting through continental collisions, mountain building, erosion, and reformation. Durable witnesses carrying unbroken memory across geological time. Some crystals form in living organisms. Bones and teeth are crystalline calcium phosphate called hydroxyapatite. Mollusk shells contain crystalline calcium carbonate in forms called aragonite and calcite. According to biomineralization research, organisms control crystal growth with remarkable precision, creating structures of specific size, shape, and orientation. Your bones are living crystals, constantly dissolving and reforming, remodeled by cells throughout your life. Pearls form when mollusks deposit layers of aragonite crystals around irritating particles. Life and crystal merge. Biology commanding geology. Organisms becoming mineral architects. Soft tissue commanding hard structure. The division between living and non-living blurring at boundaries. Snowflakes demonstrate that beauty requires no audience. Each flake forms in clouds, unseen, following the same hexagonal rules, creating elaborate branching patterns during its fall. Most land in remote areas, melt instantly, or fall into oceans, never witnessed. According to atmospheric science research, an estimated 1 septillion snow crystals fall each year worldwide. Each is geometrically complex, each unique, yet most exist and vanish without human eyes ever seeing them. Beauty arises, whether observed or not. Order emerges in darkness and solitude. Perfection requires no witness. Nature creates intricate forms for no purpose, simply because physical laws allow it. Crystals grow on the ocean floor at hydrothermal vents. Superheated mineral-rich water erupts from cracks where tectonic plates spread apart. As this water mixes with cold seawater, dissolved minerals precipitate, forming chimneys of crystalline sulfides and other minerals. According to deep-sea research, some chimneys grow several feet per year, fast by geological standards. These structures host unique ecosystems dependent on chemical energy rather than sunlight. Crystals forming in absolute darkness, in crushing pressure, in toxic fluids, yet following the same geometric rules as crystals forming in sunlit caves, proving that order transcends environment. Quartz crystals can contain liquid and gas inclusions. Sometimes during formation, small pockets of the fluid from which the crystal grew become trapped inside as the crystal seals around them. According to fluid inclusion research, these trapped samples preserve chemistry from ancient environments, sometimes containing water that last flowed millions of years ago. Some inclusions contain bubbles that move when you tilt the crystal. Liquid and vapor trapped together, mobile within their solid prism. Ancient water sealed in stone. A geological time capsule. History preserved in tiny chambers within transparent crystal. Crystals can form in human bodies sometimes. Kidney stones and gallstones are unwanted crystalline formations. Gout causes uric acid crystals to form in joints, creating painful inflammation. According to medical research, these biological crystals follow the same thermodynamic principles as geological crystals, forming when solutions become supersaturated. The body normally prevents spontaneous crystallization. But when chemistry becomes imbalanced, minerals precipitate. These are crystals in the wrong place. Order emerging where disorder would serve better. Proof that crystallization is a universal chemical process, occurring whenever conditions permit, regardless of whether the environment is a cave or a kidney. The Hope Diamond is famous partly for its unusual blue color and partly for its size, weighing 45.52 carats. It's one of the largest blue diamonds known. According to gemological research, its blue color comes from trace boron atoms in the crystal structure. Natural blue diamonds are exceptionally rare, formed under specific conditions deep in Earth's mantle. The Hope Diamond has changed hands many times, been recut, and accumulated legends of curses. But it's simply crystallized carbon with boron impurities. Geometry and chemistry creating beauty, humans then layered with meaning and myth. Some crystals show asterism, a star-shaped reflection of light. Star sapphires and star rubies contain needle-like inclusions of rutile aligned along specific crystallographic axes when cut in cabochon shape. Light reflecting from these oriented inclusions creates a six-rayed star that seems to float on the surface, moving as the stone moves. According to gemology research, this requires precise orientation of inclusions during cutting. The star exists because of imperfections aligned by crystal structure, beauty emerging from flaws arranged in geometric order, mistakes becoming features, impurity creating magic. Halite crystals sometimes form intricate cubic hopper crystals. When salt water evaporates rapidly, crystals grow faster at edges than in centers, creating hollow cubic forms with stepped sides. According to crystal growth research, this happens because atoms attach more readily to corners and edges, where they can bond with more neighbors. The resulting crystals look like geometric staircases, cubic pyramids, or elaborate frameworks. Rapid growth prevents filled-in cubes, creating delicate skeletal structures. Speed defeats completeness. Haste produces hollowness. The same conditions that would create solid cubes given time produce intricate frameworks when rushed. Crystals can record multiple growth events in zones. Many crystals show concentric layers of slightly different composition or color, like tree rings. According to petrology research, each zone represents a growth episode, possibly separated by long dormant periods. Changes in the chemistry of surrounding fluids create the zoning. Analyzing these zones reveals the history of conditions during formation. Temperature changes, pressure changes, chemical changes. The crystal becomes a layered record, an archive of its own creation. Autobiography written in chemistry, time made spatial, sequential events transformed into simultaneous nested structure. Geodes are like time capsules. The hollow center preserves the geometry of whatever cavity existed in the original rock. The crystals growing inward record the chemistry of groundwater that filled that space, sometimes millions of years ago. According to geochemistry research, some geodes contain water that has been sealed inside since formation. Pristine samples of ancient groundwater. Opening a geode releases that water for the first time in eons. Breaking the geode means ending the preservation, accessing the ancient, but destroying the seal. Knowledge requiring sacrifice. Some crystals are radioactive. Uraninite contains uranium oxide. Autunite contains uranium and calcium. According to radiation geology, these crystals emit alpha particles, beta particles, and gamma rays as uranium atoms decay. Radioactive crystals can damage other crystals stored nearby, creating dark halos in minerals like mica, tiny discolored circles where radiation altered the crystal structure. These pleochroic halos provide evidence of radioactive decay occurring over millions of years. The crystals are slowly transforming themselves through nuclear decay, uranium becoming lead, energy releasing as radiation, matter becoming lighter matter over geological time. Crystals can form on falling raindrops. Hailstones form when updrafts in thunderstorms carry water droplets upward into freezing layers. Ice crystals form around a nucleus and grow as the hailstone circulates through the storm, accumulating concentric layers of ice. According to meteorological research, cutting a large hailstone in cross-section reveals clear and opaque layers like an onion, each layer representing one trip through different parts of the storm. The hailstone grows until it's too heavy for updrafts to support. Frozen history of a violent storm journey. Bismuth can form spectacular stepped crystals. When molten bismuth cools and crystallizes, it forms distinctive hopper crystals with colorful oxide layers, creating geometric spiral staircases. According to materials science, the colors come from thin oxide films that create interference patterns, shifting from yellow to blue to pink. Bismuth is one of the few metals that expands upon solidification. Like water, artificial bismuth crystals grown from melts develop elaborate architectures through rapid cooling. Technology and artistry merge. Science creating accidental beauty. Chemistry producing unintended aesthetics. Order generating surprise. We now understand that crystallization is one of nature's fundamental organizing principles. From atoms to galaxies, matter tends toward order when conditions allow. Crystals represent the most obvious expression of this tendency. Visible, touchable proof that chaos can become structure. That disorder can become pattern. Every crystal is a small victory of order over entropy. Temporary, but real. And yet, entropy ultimately wins. All crystals will eventually dissolve, erode, or transform. The order is temporary but beautiful while it lasts. Structure emerging briefly before returning to disorder. A dance between organization and chaos. Ancient peoples valued crystals for beauty and believed they held powers. According to archaeological evidence, humans have collected, traded, and treasured crystals for tens of thousands of years. Clear quartz was carved into lenses and spheres. Jade was more valuable than gold in some cultures. The science of crystallography only began in the 17th century. but human appreciation of crystals is ancient and universal. People recognized something special about these regular, transparent, colorful stones even without understanding atomic structure. Beauty preceded understanding. Appreciation preceded explanation. Wonder came first. Crystal healing beliefs lack scientific support. While crystals do have measurable physical properties like piezoelectricity and optical effects, research finds no evidence they emit healing energies or vibrations detectable by the human body. According to studies published in medical journals, any perceived benefits from crystal healing likely come from placebo effects. Crystals are fascinating for what they actually are: ordered arrangements of atoms, demonstrating physical principles. Without needing supernatural properties, their real physics is remarkable enough. Truth is more interesting than myth. Though myth is more comforting than complexity, crystals can survive extreme events and preserve evidence. Compressed quartz from meteor impacts, high-pressure minerals from deep subduction zones, crystals containing ancient atmospheres trapped in fluid inclusions. Each sample tells a story of considerable conditions and narrow survival. According to high-pressure geochemistry research, some crystals form only at pressures exceeding 30,000 atmospheres, depths of 60 miles or more, then ride back to the surface in volcanic eruptions. They shouldn't exist at surface pressure but persist metastably, frozen in high-pressure forms, unstable yet durable, carrying evidence of realms unreachable. Synthetic crystals enable modern technology. Silicon crystals for computer chips, sapphire crystals for scratch-resistant watch faces and smartphone screens, yttrium, aluminum garnet for lasers, lithium niobate for telecommunications. These materials must be synthesized because natural versions are too impure or rare. According to materials science, growing large, perfect crystals requires precise temperature control, ultra-clean environments, and days to months of slow growth. We've learned to outpace nature through technology, accelerating geological processes, controlling what nature leaves to chance, engineering order with deliberate intent rather than accidental occurrence. Some crystals exhibit thermochromism, changing color with temperature, according to solid-state chemistry. This occurs when heat energy affects the electronic or molecular structure. Liquid crystals in mood rings change color with skin temperature. Some minerals show subtle color shifts with heating. The color changes are reversible. Cooling returns the original color. Temperature becomes color. Heat becomes hue. Thermal energy transforms into optical properties. Another example of energy and matter interconverting. Another demonstration that properties we perceive as fixed are actually fluid, responding to environment, adapting to conditions. Crystals connect the quantum to the visible at atomic scales. Quantum mechanics governs electron behavior in crystal lattices. These quantum properties determine conductivity, color, magnetism, and optical properties. According to solid-state physics, understanding crystals required developing quantum mechanics in the early 20th century. The colors you see in gems, the electricity flowing through silicon, the magnetism in lodestone, all emerge from quantum phenomena. Crystals make quantum mechanics tangible, bringing the strange world of probability waves and electron orbitals into everyday experience. The invisible made visible, the abstract made concrete. Mystery made manifest. Ice is a mineral according to the formal definition. It forms naturally, has a definite chemical composition, and possesses a crystalline structure. According to the International Mineralogical Association, frozen water meets all criteria for mineral status. This means glaciers are technically rock formations, icebergs are floating rocks, and snowflakes are mineral crystals. The classification seems strange because ice melts easily, but mineralogy defines minerals by structure and composition, not stability. Ice is temporary rock, ephemeral mineral. Geology's most fragile expression. Order with an expiration date built in. Crystals can self-repair under certain conditions. According to materials science research, some crystals can heal defects when heated. Atoms gain enough energy to migrate and rearrange, allowing dislocations and vacancies to anneal. This process requires temperatures high enough for atomic mobility but below melting. Self-healing occurs slowly, atoms shifting one at a time toward more stable positions. The crystal doesn't know it's damaged or want to repair. It simply follows thermodynamic gradients toward lower energy states. Healing is physics, not intention. Recovery is inevitable given time and temperature. Some crystals form only in meteorites, never on Earth. According to meteoritics research, these minerals require conditions, considerable pressure during impact, or chemical environments not found on Earth, or formation in the early solar nebula. Studying these exotic crystals reveals conditions in space and in early solar system formation. Each meteorite is a sample from beyond Earth, carrying minerals that formed in alien environments. These crystals are extraterrestrial visitors, cosmic samples delivered naturally, pieces of other worlds, evidence that crystallization is universal, occurring wherever matter and energy interact. Interstellar objects, like 2I Borisov, which visited our solar system in 2019, may contain ice crystals formed around distant stars. According to observations from international observatories, analyzing such objects might reveal chemical signatures from alien stellar environments. Crystallization occurs throughout the universe, in all solar systems, around all stars, following the same physical principles everywhere. The patterns differ based on local chemistry, but the principle, atoms arranging in ordered structures, is universal. Physics transcending location. Order emerging wherever conditions allow. The same laws governing distant systems and our own. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Crystals form and dissolve. Rocks erode and reform. Mountains rise and fall. All are circles, cycles, endless transformations, like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast geological story. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like crystals silently growing in dark caves. Unhurried, unresisting, simply existing. We're almost there now. Crystals teach patience. Formation takes time. Days, years, millennia, eons. Rushing produces inferior results. perfect crystals require stable conditions maintained across long periods. According to geological timescales, the most beautiful crystals often took the longest to form. Large quartz crystals in pegmatites grew over millions of years. Giant selenite crystals in Nika's caves needed 500,000 years. Time cannot be shortcut without cost. Patience creates perfection. Haste creates flaws. This seems true beyond geology. A principle crystals demonstrate, but don't create. Crystals demonstrate that order is natural, left alone under the right conditions. Matter organizes itself, no designer needed. No intelligence required. Just atoms following physical laws, finding stable arrangements, creating pattern from randomness. Crystals prove that complexity can arise from simplicity, that beauty emerges from basic rules, that organization is not imposed from outside, but arises from within. This suggests something about the universe's nature. Order is not rare but common, not special but inevitable, not requiring explanation, but being explanation itself. Crystals show us that strength and beauty coexist. Diamond is both the hardest natural substance and one of the most visually striking, the same properties that make crystals durable. Strong atomic bonds, ordered structure, also make them aesthetically pleasing. According to materials science, structural integrity and visual appeal both arise from the same source, optimal atomic arrangement. Perhaps beauty is efficiency, elegance is function, aesthetics is physics. Form follows function, even in geology, creating beauty as byproduct of stability. Crystals reveal that transparency is rare and valuable. Most matter is opaque. Light gets absorbed or scattered by disorder. Crystals can be transparent because their ordered structure allows light to pass through without scattering. According to optical physics, perfect transparency requires perfect order. The clearest crystals are the most ordered. Transparency equals purity, equals organization. Perhaps metaphorically too. Transparency requires order. Honesty requires structure. Clarity needs foundation. What allows light through also provides strength. Openness and integrity connect. Crystals illustrate that imperfection creates uniqueness. Two quartz crystals might be chemically identical, but have different inclusions, different faces, different growth histories. According to mineralogy, every crystal is unique in some way. The imperfections, missing atoms, foreign atoms, dislocations, create individuality. Pure perfection would be uniform and identical. Deviation creates distinction. Flaws make recognition possible. Perhaps this applies broadly. Differences arise from imperfections. Identity from irregularity. Character from chaos infiltrating order. Uniqueness requires impurity. Crystals demonstrate that structure determines properties. Salt tastes salty because of how sodium and chloride are arranged. Diamond cuts steel because of how carbon atoms bond. Quartz keeps time because of its crystal structure. According to solid-state physics, macroscopic properties emerge from microscopic structure. How atoms connect determines what materials do. Structure is destiny. Arrangement is fate. This principle extends. How parts relate determines what wholes can do. Organization matters more than components. Configuration creates capability. Crystals show that small changes cascade. Adding one impurity atom per 1,000 changes quartz from clear to purple. Slight temperature shifts during growth change crystal habit. Minor pressure variations create different minerals from the same chemistry. According to phase diagram research, small differences in conditions produce large differences in outcomes. Sensitive dependence on initial conditions applies to crystallization. Tiny causes, large effects, small inputs, significant outputs. Perhaps this principle generalizes small changes compound. Minor factors matter. Details determine direction. Crystals illustrate that dissolution and creation are paired. Caves form as limestone dissolves. Then stalactites grow from that same dissolved calcite. Erosion releases mineral grains that later cement into new rock. According to geochemistry, the materials don't vanish, but transform. Moving from one structure to another, creation requires dissolution. Building needs breaking. New forms arise from old forms' endings. Perhaps this cycle applies universally. Growth feeds on decay. Birth requires death. Renewal demands ending. The cycle turns eternally. Crystals teach that boundaries matter. Crystal faces represent where growth stopped because conditions changed. Inclusions mark where foreign material entered. Zoning shows where chemistry shifted. According to crystal growth theory, boundaries record transitions, mark changes, preserve history. What lies between is as important as what lies within. Edges define shapes. Limits create identity. Perhaps boundaries generally create rather than constrain, defining rather than restricting, enabling rather than preventing. Limitation creates form. Crystals demonstrate that information persists. Compressed quartz preserves evidence of impacts long after craters erode. Oxygen isotopes record ancient temperatures. Uranium-lead ratios measure time. According to geology, rocks remember. Crystals carry messages across epochs, encoding history in structure and chemistry. Information doesn't vanish but transforms, moving from event to record, from process to product. Memory takes many forms. The past persists in present structure. Time leaves traces that survive time's passage. History becomes geography. So yes, crystals reveal profound truths about our world. They show that order emerges naturally, that beauty arises from simple rules, that time and patience create complexity, that structure determines function, that small changes matter, that boundaries define, that the past persists, that dissolution and creation balance. These aren't lessons crystals teach intentionally. They have no intention, but principles we recognize by observing them. The universe demonstrates its rules through every crystalline structure, writing its laws in mineral code. Crystals remind us that we're made of minerals too. Your bones are crystalline calcium phosphate. Your blood contains iron. Your nerves use sodium, potassium, and calcium ions flowing through channels. According to biochemistry, you're partially mineral, partially crystal, partially rock. The line between living and non-living blurs. Your animated geology, thinking stone, conscious crystal. Life didn't escape the mineral kingdom. It incorporated it, built with it, became it. You are Earth becoming aware of itself. Crystals suggest that perfection is temporary. Even diamonds eventually decay through radiation damage and oxidation. All crystals will someday dissolve or transform. According to thermodynamics, order inevitably gives way to disorder. Entropy always increases. Structure is temporary. Organization is provisional. The second law guarantees dissolution, yet crystals form anyway, creating temporary order against the gradient. Local organization despite universal decay. Perhaps the meaning is in the temporary existence. Beauty in transient structure. Value in ephemeral order. Crystals show that information flows in multiple directions. We usually think of cause and effect as linear. Past causes present. But crystals demonstrate circular causation. Their structure determines their properties. But their properties also reflect their formation conditions. According to systems theory, feedback loops operate everywhere. Effect becomes cause. Output shapes input. Perhaps this applies beyond geology. Understanding works both ways. Observer and observed shape each other. Knowledge transforms both knower and known. Relationship creates reality. So could sleepy science reveal truth about crystals? Yes. Through understanding that minerals aren't mystical but are fascinating in a different way. They're proof that physical laws naturally generate beauty and complexity through simple rules applied across time. Reality surprises us more than superstition ever could. Scientific truth holds more wonder than ancient myth. We've learned that crystals are records of time, products of patience, demonstrations of natural law, intersections of chemistry and beauty, bridges between quantum and classical. Crystals whisper that we're temporary too, like them. We're ordered structures persisting for a while against entropy's pull, like them. We're specific arrangements of common elements, like them. We'll eventually dissolve. According to physics, humans and crystals both fight the second law temporarily, creating local order while increasing universal disorder. We're similar. Temporary structures in eternal flux. Brief organizations in endless chaos. Fleeting patterns in permanent flow. Kinship exists between thinking flesh and silent stone. Crystals suggest beauty needs no purpose. They form because physics allows it, not because beauty is needed. Snowflakes are hexagonal not to please eyes, but because water molecules bond that way. According to crystallography, aesthetics is accidental. Beauty is byproduct. Yet we respond to it. We value symmetry, transparency, color, regularity, properties crystals display. Perhaps beauty is recognizing order, appreciating organization, celebrating structure. Aesthetic response might be pattern recognition, finding meaning in arrangement. Crystals demonstrate that complexity arises from simplicity. 14 lattice types, 32 symmetries, yet infinite variation. Simple rules, complex outcomes. According to mathematics, constrained systems generate diversity. Limits enable creativity. Boundaries permit freedom. Perhaps this principle extends structure, allows innovation. Rules enable improvisation. Constraints create possibilities. The most interesting results emerge not from chaos but from order's edges, where pattern meets variation, where rule permits exception, where structure allows surprise. Simplicity generates sophistication. Crystals reveal that change is slow. Mountains don't rise suddenly. Crystals grow grain by grain. According to geology, Earth changes gradually, incrementally, imperceptibly. Only across vast time do transformations become visible. Perhaps patience applies. Universally, real change happens slowly. Genuine growth takes time. Lasting transformation requires duration. Quick changes reverse quickly. Slow changes endure. What forms fast dissolves fast. What forms slowly persists. Time invested determines stability. Patience creates permanence. Crystals teach that we're star children. The silicon, oxygen, carbon, and iron in crystals were forged in stellar cores, ejected in supernovas, condensed in the solar nebula, incorporated into Earth. According to cosmochemistry, you and crystals share this ancestry, made of stardust, born from explosions, condensed from cosmic clouds. The atoms in your bones and the atoms in quartz are siblings, formed in the same stellar furnaces, scattered by the same supernovas, family members in the cosmic tree. Crystals whisper that silence holds wisdom. They form without sound, grow without announcement, persist without declaring. According to geology, the quietest processes often matter most. Erosion works silently. Crystallization makes no noise. Tectonic plates creep soundlessly. Perhaps silence generally accompanies depth. Profound change happens quietly. Real growth proceeds silently. Important processes work without fanfare. Loudness indicates surface. Silence suggests depth. Noise is temporary. Quiet is enduring. Listen to silence. Crystals suggest that interconnection is fundamental. Atoms bond to atoms. Crystals grow from surrounding solutions. Minerals form from redistributed elements. According to systems science, nothing exists in isolation. Everything connects to everything. Separation is illusion. Boundaries are permeable. Distinctions are artificial. Perhaps interconnection is reality's fundamental nature. Separation is perception. Connection is truth. Isolation is impossible. Relationship is inevitable. We're all part of the same system. Different expressions of unified process. Variations on common theme. Crystals demonstrate that information is preserved. Growth bands record history. Isotopes mark time. Inclusions capture environments. According to information theory, the universe remembers. Nothing is truly lost. Every event leaves traces. Past influences present. Memory persists in structure. History lives in form. Time survives in space. Perhaps nothing vanishes completely. Energy transforms. Matter reorganizes. Information redistributes. The past doesn't disappear. It changes shape, becoming structure, turning into pattern, transforming into arrangement. Crystals teach that we're process, not product. They're always forming or dissolving, growing or eroding, stable but temporary. According to process philosophy, being is becoming. Existence is transformation. Stability is dynamic equilibrium, not static state. You're not fixed but flowing, not solid but streaming, not being but becoming. like crystals. You're patterns that persist while materials flow through. Forms that maintain while contents change. Structures that endure while composition transforms. Identity is process. Self is flow. The real change isn't in crystals. It's in us. Studying them changes how we see matter, time, beauty, order. We learn that nature organizes itself, that patience creates perfection, that simple rules generate complexity, that we're made of the same stuff as rocks and stars. Understanding crystals means understanding ourselves as part of nature, not separate from it. The deep truth is kinship, connection, unity. We are stardust contemplating stardust. That's the revelation. And so, our quiet journey through Earth's crystalline wisdom comes to a gentle close. We've traveled from atoms arranging themselves in perfect order to diamonds formed under tremendous pressure, discovering along the way that patience creates beauty and time writes stories in stone. From snowflakes forming in clouds to synthetic crystals powering your devices, we've glimpsed how minerals are both ancient and modern, both natural and technological, both simple and profound. Crystals remind us that order emerges naturally from the universe itself. Much of Earth's most spectacular beauty happens in silence, in darkness, in depths we'll never visit, in timescales we can't comprehend. They reveal patience, demonstrating that the most beautiful structures require the longest growth. Without crystals, we'd have no bones, no technology, no records of deep time. By pausing to notice, we glimpse the extraordinary in the ordinary. In these final minutes, take the deepest breath you can, as deep as possible. Think about how water cycles through clouds, rivers, oceans, and rain. Everything is connected. Everything returns. Everything flows. You are part of that flow, that cycle, that eternal return, like crystals forming and dissolving across geological ages. You too are part of nature's great recycling. Atoms borrowed temporarily, structure maintained briefly. Let your entire being dissolve into the rhythm of Earth, into the breath of stone, into the patience of mountains, into stillness. If these calm stories from Earth's mineral kingdom helped you connect with deep time, ancient patience, and the beauty of natural order, a gentle like and subscribe could help another tired soul discover this peaceful rest. It might be exactly what someone else needs to finally let go and drift. One quiet tap, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight through geological time, through atomic structures, through spaces between molecules where electrons dance. You can allow these thoughts of crystals to fade now, like morning mist dissolving in sunlight, leaving only the quiet calm behind. Let your breathing deepen. Let your body feel heavier, as if gravity itself is gently pulling you down into Earth's patient embrace. If sleep comes, let it carry you like sediment settling through still water, smoothly, inevitably, into a realm where time and structure no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, crystals will still be forming in caves. Mountains will still be growing grain by grain. Atoms will still be arranging themselves in perfect order. But tonight belongs to stillness. Rest well, sleepy scientist, and remember, you are made of the same atoms as diamonds and quartz, assembled temporarily into the miracle of consciousness. Stardust, arranged briefly into the beauty of awareness. The universe knowing itself through you. One final breath, and release. Dream deeper with bedtime science. Good night.